I'm going to talk a little bit about momentum in two dimensions. And it's not very different than momentum in one dimension. So in 1D, we say that momentum is conserved as long as there is no external impulse on it. And that's true for 2D also. So we say that initial momentum as a vector equals the final momentum as a vector as long as there is no external impulse. Okay, that's important. And the reason for that is I think we say that J is equal to delta P. Okay, so if J is 0, no external impulse, there's no change in momentum. That's basically what it means. Okay, what does this mean? Well, if we look at it in 2D, and this is the sum, okay? This is the total momentum, right? This is the sum, the total momentum. So you can have two objects colliding, so the total momentum of the two before the collision equals the total momentum after the collision. In other words, if the total momentum looks like this initially, after you combine the two momenta, at the end, after, it should be exactly the same in magnitude and in direction. Now, what does it mean that momentum is conserved in both directions? Well, it means that the sum of the momenta in the x direction, okay, is equal to the sum of the momenta final in the x direction, right? So here we're going to do we can do law of cosines, we can do law of sines. It's basically not different than when we did forces. And sum of the momenta in the y direction initially equals the sum of the momenta in the y direction after the collision. Okay, that's pretty much what the conservation of momentum in 2D means. But just the main thing here is that there cannot be any external impulse. Okay, that's a nice and short and sweet. See you later.